All right, welcome everyone. We're going to go ahead and continue on. Last time we continued with mesh analysis, and now we're going to start a new network analysis technique known as nodal analysis. Now, whereas mesh analysis took a KVL approach, meaning we wrote mesh currents and then we expressed a KVL equation, a Kirchhoff's voltage law equation, looking at the sum of all voltage drops in any closed loop. We're going to now take a current approach using Kirchhoff's current law. So we're going to go ahead and be looking at nodes in our circuit and writing equations for those. Now, similar to mesh analysis, this is one of those procedural or programmatic methods for solving your circuit that as long as you step through the steps and apply those steps correctly, we're going to get the correct answer no matter what. So it's kind of really nice in that aspect. So now I'm starting off with this circuit, and this circuit looks like, oh, it's kind of big for a beginner circuit, but I've done it this way because it's going to do a good job of illustrating for the first time how we apply the nodal analysis technique. So let's start off with steps. Steps are always nice for doing this. Okay, for our first step in this nodal analysis technique, we're going to start off by labeling a reference node. Label reference node. And the way we're going to go ahead and label this reference node is by using the ground symbol. Now, we're going to go ahead, pick a point on our circuit. You can pick any point and you can label it as the reference node. It doesn't matter. However, some points of your circuit will end up being more easy for the sake of writing the equations. So I'm going to pick a point on this circuit that looks to me like it might be a great place to label as ground. Now on this circuit, I see over here, I'm like, voltage drop there, voltage drop there. I got two current sources going up. You know what's a great place that looks like to me is right here. I'm going to label this as my reference node. And when we label something as ground, what we're really saying is for all practical purposes, this is going to be considered 0 volts for the sake of solving this circuit. Okay, wherever you place this ground symbol is going to be 0 volts. Okay, so that ground symbol might be kind of a little new. Okay, now that gets done with our first step. Let's move on to our second step. Our second step is going to be assign node voltages. All of them but the reference node. Okay, so we're going to go ahead and we're going to pick every single place on this circuit that should have a different voltage. Okay, now we already labeled the reference node. This is 0 volts. This is also 0 volts. They're connected with a wire. This over here is 0 volts. This is 0 volts. In fact, along this wire at all of these points, you can consider to be 0 volts. So none of these along the bottom is going to have a different voltage. However, we do have a different voltage at, say, this point. Over here we have a different voltage. We're just going to label this as V1. We don't know what these voltages are yet. This is going to be what we're solving for, but I know that this point right here, it's going to have a different voltage than over here. Same thing with this point over here. I have a different voltage here. I know that because I will get a voltage drop across this 500 ohms. So I'll label this as V2 and over here as V3 because this point has a different voltage as well. And we are done. Every single point of this circuit is now labeled with some voltage. 0 volts along the bottom, and at all of these different points we have a V1, a V2, and a V3. Okay, we don't have a different voltage here because this is just V1. Same thing over here. This is just V3. We've already covered those with these nodes where we have current entering and splitting. Okay, so that takes care of step 2. Assign our node voltages. Okay, our third step is going to be apply KCL to each non-reference node. Okay, so for each one of these, we're going to apply KCL for V1, for V2, and V3. And we're going to write out an equation using KCL for each one of those. So let's go ahead and let's do that. Let's start with our node V1. Now, to make this easy, I'm going to break this down into 2 steps. The first one is, let's just go ahead and draw some currents over here. And I'm going to pick these currents so that they're easy to write. In other words, I look at this wire over here, and if you notice, I have a constant current source of 3 milliamps going up and to the right over here into this node. So I'm going to label my current to go this way. Okay, now for the sake of the current that's going through this 500 ohms, whether it's leaving or entering V1, again, I'm going to go ahead and pick a direction that makes sense for the sake of writing this equation more easily. Over here, I have V1 over here. I have ground on the other side. So I have 0 volts on this side of the 500 ohm, and I have V1 on this side. You know what? I'm going to write my current to go down. And the reason is I'm making the assumption that V1 is larger than 0 volts. That may not be true. We'll find out later. But we have to pick a direction. It doesn't have to be correct. But it's going to allow us to write this equation, and then we'll find out which way the conventional current actually goes. Okay, same thing over here. I have V1 on this side, I have V2 on this side. I need to pick the current to either be entering the V1 node or to be leaving the V1 node. Now in this case, because I have 2 voltages involved, it makes no difference. The equation's not going to be any easier or more difficult to write regardless of the direction I pick. So I'm just going to pick it to be leaving V1. I'm going to have it head off in this direction. Okay, now at this point I need to label these currents so I can write an expression, a KCL expression. So over here, this current that's leaving the 3 milliamp constant current source and entering into V1, well, this is a constant current source. We're going to always get 3 milliamps going in this direction regardless of what the rest of the circuit's doing. So I'm just going to call this 3 milliamps. Okay, now this current that's going down, I'm going to go ahead and just call it IA. I don't know what it is yet. Same thing with this third current over here, this one that's leaving V1. I'm just going to call it IB. Okay, now that I have three currents, which are the only currents involved with this V1 node, I can go ahead and express this in terms of KCL. The sum of all currents entering a node equals the sum of all currents leaving that same node. Well, I have 3 milliamps entering. Nothing else is entering. So this must be equal to the sum of the currents leaving. In other words, IA plus IB. Okay, but I don't want to leave my currents in just terms of IA and IB, so I want to express these currents given what I have here. Now notice I have 500 ohms. That's given. Do I have voltages? Yeah, I have labels for these voltages. I have 0 volts on one side. I have V1 on the other side. So what's the voltage drop across this 500 ohms? Well, it's just V1 minus 0 volts. Or in other words, it's just V1. So if I want to write what IA is equal to, I can just invoke Ohm's law here and say that IA is equal to the voltage divided by the resistance, or V1 divided by 500 ohms. So let's go ahead and let's write that out. IA equals V1 divided by 500 ohms, right? Look at how I wrote this current. This current is going down. And one thing that I always say, and I probably sound a little repetitive at this point, current always goes from a higher voltage to a lower voltage. I'm working off of the assumption that V1 is larger than 0 volts, and that's fine. I'm going to get a valid and correct equation for that current using Ohm's law if I say that V1 is the voltage drop across this 500 ohms. Let's do the same thing for IB. Now, IB is mildly trickier. I only say that because we have two unknown voltages over here. I'm not working with ground. So my voltage drop across this 500 ohms, well, again, if I'm assuming that current goes from a higher voltage to a lower voltage, I'm just going to say that V1 minus V2 is the voltage drop across the 500 ohms. Okay? Use polarity to help you out. Remind yourself, current goes from a higher voltage to a lower voltage. Now I can just say plus V1 minus V2 is the voltage drop across the 500 ohms. Okay, so I didn't have to intuitively figure anything out here. I just said current goes from a higher voltage to a lower voltage, and I used the polarity to help me correctly express the voltage drop across the 500 ohms. If you do it this way, you'll never mess this up. Okay, so we can say that IB is equal to plus V1 minus V2 divided by 500. Okay, if I had written the current to go in the other direction, my assumption would have been different. I would have been implying that my V2 is larger than V1, so I would have written a plus sign over here, and I would have written a minus sign over here. I would say plus V2 minus V1 divided by 500. That's if I would have picked my current direction to go this way, okay? If I would have picked IB to go in this direction, which I totally could have done. There was nothing to help me say that this current is actually going one way or another. So it doesn't matter as long as you write the equation correctly, given the directions that you pick for your currents, okay? But in this case, I picked it to go to the right. I'm assuming this is higher than this. So I wrote a plus here, minus here, and then I used the polarity to help me out. Plus V1 minus V2 divided by 500. So at this point, I have a KCl expression, and I have all of my currents written in terms of V's and my resistances. So let's go ahead, plug these back into here, and we get a finished KCl expression. Three milliamps therefore equals V1 divided by 500 plus, plus V1 minus V2 divided by 500. Okay, so I now have my first equation. Okay, that takes care of node 1. Let's go ahead, let's do the same thing for node V2. If I just lay another piece of paper over this, I end up bleeding the marker through. So I kind of need to fold it if I want to reuse my drawing. I am not a master of origami. Okay, now for writing this next equation for node V2, I'm going to go ahead and use a different color. You'll see why in a second. Okay. Now, same thing over here. I need to go ahead and write some currents. Now, I can pick them to go in any direction, but I will try to pick them such that it makes the equation easier to write. Now, the only one that actually makes it easier to write is to actually pick this 1K, the current through them, to be going down. And that's because I'm assuming that V2 is higher than our reference node. Now, as for the current going through this 500 ohms, again, I can pick it to go to the left, to the right, doesn't make any difference. I'm going to pick it to go to the left, and I'm going to pick this other one to go to the right. Okay, so I picked my current directions. Now I need to label these guys. I'm going to call this IA, I'm going to call this IB, and I'm going to call this IC. And now you might be thinking to yourself, you're like, but all the currents are leaving the node. Well, this is completely fine to write because the sum of all currents entering a node must equal the sum of all currents leaving that same node. But if I have all my currents leaving a node, that just means that all of those currents are going to add up to 0. I can totally have a negative current. Current just means that the current direction is actually going in the opposite direction. So this is completely valid to write it this way. And so I'm going to just write IA plus IB plus IC is equal to 0. Okay. Another way of thinking about this KCl equation is conservation of charge. I don't have any new electrons being introduced to this node, and I have no electrons that are just leaving except through these paths. So This equation, completely valid. Let's go ahead and write out what each one of these currents is. So IA, and notice, before I write out IA, notice that I've reused IA, IB, IC. Don't get confused that this IA is the same as this IA, even though I'm using the same notation that I did for this equation. I'm reusing IA, but they're not the same. I'm just using this as an intermediary step in order to correctly write the equation. Once I solve the equation and substitute back in my IAs, I don't use them anymore. So I'm just using them for this interim step. Okay, so what's IA equal to? Well, notice now that I picked my current direction to go to the left. Current always goes from a higher voltage to a lower voltage. So now I'm working off of the assumption that it's plus V2 minus V1 is my voltage drop across this 500 ohm resistor. So I can say plus V2 minus V1 all divided by 500 is the current IA. Plus V2 minus V1 divided by 500. Okay, so I'm done with IA. Let's go ahead and write IB. IB is going to be the easier one in this case because I'm assuming this is 0 volts, so the voltage drop across the 1K is just this V2. So I can say IB is equal to V2 divided by 1K. And I'm done with IB. Okay, let's go ahead. Let's write out IC. Okay, what's the story with IC? Well, again, I have my current direction going to the right, so I'll go ahead and say current goes from a higher voltage to a lower voltage, plus V2 minus V3 is that voltage drop. And divide it by the resistance 500 gives me the current IC. So now I have my three currents in terms of V's and ohms. All right, let's plug those back into our equation and we'll get our second equation. And all of that's equal to 0. So now I have my second equation over there. Perfect. Okay. Now, I'm done with my node V2 equation. We need to write out our node V3 equation. Okay. So I'm going to switch and use a different color for this one as well. And to help me out here, again, I'm going to go ahead and write some currents in here. Try to pick them such that they make the equations a little easier to write. So in this case, the only one, actually two of them that stand out to me, I have a constant current source. I get a constant 4 milliamps entering the node from this direction. So let's go ahead and put in a current going in that direction and call it 4 milliamps. Now, I could totally write this current to go in the other direction. I could write it to go to the right, but I would have to say minus 4 milliamps because this constant current source is causing the current to flow to the left. So if I were to pick the arrow to go to the right, I'm going to have to write a minus over here. But I try to keep everything as much positive as possible, just to make life a little easier so I have less minus signs floating around and less, I kind of think of them as double negatives. And so I'm just going to pick it to go in the same direction as the constant current source, so I can very simply write 4 milliamps on there and be done with it. The other one that stands out as being easy to write is, again, I have my reference node. I have 0 volts over here. Let's just assume V3 to be positive. So I'm going to pick this current to go down. And the current over here through this 500 ohms doesn't matter. I can pick it to go to the left, pick it to go to the right. Makes no difference to me. I'm going to pick it to go to the left. All right, let's go ahead and label these. I'm going to reuse my same labels because they aren't going to manifest themselves in this equation anyways, so it doesn't matter. It's just an interim step to help me write out my node equation. Let's go with IA, IB. Okay, so IA referring to the top one that's going to the left, and IB referring to this one through the 500 going down. All right, let's go ahead and write out KCL. The sum of all currents entering a node equals the sum of all currents leaving that same node. I have 4 milliamps entering. And that must be equal to everything that's leaving, which is IA plus IB. All right, now let's go ahead and write out what we don't have, which is IA and IB. IA equals, well, again, I'm going to use the current to help me out. Current always goes from a higher voltage to a lower voltage because IA I wrote as going to the left. So I'm assuming that V3 is higher than V2. Notice that's different than what I did for the previous step. It's okay because I'm going to get these 3 equations and each one is valid, and I'll end up solving that system. So perfectly fine, just like I did before, that for expressing this V3 node equation that I picked it differently than what I did in the previous steps. And I've tried to illustrate that each one is kind of an independent thing by using a different color here. Okay, these are just tools to help me get this equation. So I can now say IA is equal to plus V3 minus V2 all divided by 500. Okay, let's go ahead and now let's do IB. IB is a little easier because we only have 1 voltage involved. We assume that this side on the reference node is 0 volts, and we'll just take V3 to be positive because we wrote our current going downward. So I can just say IB equals a positive V3 divided by 500. And I'm done with those currents. Let me plug them back into my KCL expression here, and I will get my last equation. 4 milliamps is equal to V3 minus V2 divided by 500 plus IB, which is V3 divided by 500 and I'm done. Okay, so at this point, I now have 3 equations. I have 3 equations and I have 3 unknowns. My only unknowns in these equations are V1, V2, V3. Everything else is known. Everything else is in terms of resistances and currents. Resistances and currents. This one came out to be 0 because we picked them all that they were leaving that node. Same thing over here. Okay. So at this point, all we have to do is solve this system of equations. Now, when I did mesh analysis, I already went over our methods that we had available to solve these systems of equations. So I'm not going to bother doing substitution or adding these equations or plugging it into a matrix. Instead, I'm just going to write out what these values ended up being. V1 equals 1.33 repeating volts. V2 came out to be 1.166 repeating volts. And V3 ended up being 1.5833 repeating volts. Let's go ahead and plug these back into our circuit and see what all of this means. Okay, I had a 3 milliamp constant current source. Four milliamps. These two up here were 500s. 500 ohms, 1K, 500, and 500. Cool. Okay. Now over here was our V1. Over here was our V2. And I'm just going to round each one of these out to 2 decimal points. And our V3 was 1.58 volts. Cool. Okay, so what did we find out here? Well, I mean, we found out the voltage. That's huge. We can figure out everything from this circuit now. Now, our initial assumption was that over here was 0 volts. Well, check out what we got. Our assumption was good. This is the lowest voltage point of this circuit. All of these other ones are positive with respect to this point. So as far as our currents, let's look at what our actual currents are doing. Okay, current always goes from a higher voltage, positive, to a lower voltage, lower. Perfect. What about our current going over here? Well, this is almost given by the problem. It practically is because we have a constant current source. Okay, what about over here? Well, current always goes from a higher voltage to a lower voltage. Which is the higher one of these numbers? 1.33. So it's going in this direction. Okay, let's look over here. 1.17 is higher than 0 volts. All right, let's look at this 500 ohms. We have our higher voltage over here. 1.58 is higher than 1.17. Okay, what about over here? Well, this down here is 0 volts, so 1.58 is definitely larger than that. And our constant current source over here is telling us the current's going in this direction. So this is our conventional current. Now, as far as solving for any one of these currents, easy. This is 3 milliamps given by the problem. Over here is 4 milliamps given by the problem. Let's go ahead and let's look at this 500 ohms. Well, I have 1.33 volts on this side. I have 0 volts on this side. So I can say that my voltage drop across the 500 is 1.33 volts. So if I want to know what this current is, it's 1.33 divided by 500. Let me pull up my calculator over here. 1.33 divided by 500 gives us 2.66 milliamps. Let's call that 2.7 milliamps. I'll write it over here on the side. 1.33 volts divided by 500 equals 2.7 milliamps. Okay, what about this other one? Use the same technique we used earlier. Current always goes from a higher voltage to a lower voltage, hence this side must be higher than this side. And if I want to know the voltage drop across this 500 ohms, I can just say plus 1.33 minus 1.17 equals what? Well, 1.33 minus 1.17 gives us 0.16 volts. Okay, so my voltage drop across this 500 is just 0.16 volts. So now I can say 0.16 divided by 500 gives me my current. Zero 0.3 milliamps. I'll just go ahead and round that out. All right, perfect. Well, look at the KCL expression. I got 3 milliamps entering, I got 2.7 leaving, and 0.3 leaving. 0.3 plus 2.7 is 3 milliamps. Actually, I didn't show where I solved the system for voltages. Yeah, I skipped over that. I talked about the solving systems previously with the mesh analysis, and I went over all the techniques that are available to us, and I did some adding on that. It takes some time. I don't want to take up 15-20 minutes of class solving a system of equations. Okay, so now let's look at this other one over here. I have this 1K, I have 1.17 volts across him. So let's do 1.17 divided by 1,000 gives us 1.17 milliamps. I'll just call that 2 milliamps. Okay, same thing over here. Use the current to help you out. This side is higher than this side, so I say plus 1.58 minus 1.17. 0.58 minus 1.17 gives me a 0.41 voltage drop across that 500. So divide it by 500, and I get 0.8. Okay, I have another KCL over here, so I can verify whether that, makes sense. 0.8 plus 0.3. All right, that equals 1.1. That's because of the rounding. If I would have taken these out, I would have been a little closer to 0. But definitely still correct. And the rest of these are correct. So Nodal analysis gets us our voltages. From our voltages, we can infer everything we wanted to know about this circuit. So kind of similar to that mesh analysis technique, except we're taking a KCL approach to the solution as opposed to a KVL. Where did I get my 1.2 milliamps? That's going to be 1.17 divided by 1K, right? Because I have 0 volts down here and I have 1.17 volts here. So if you want to go ahead and use that trick to help you correctly write the voltage drop across them, you can just say that current goes from a larger voltage to a lower voltage. Hence, I have plus 1.17 minus 0 volts. And that is still completely correct. This last 500 ohms, yeah, okay. Why not? There's one left. 1.58 divided by 500 gives us 3.16, 3.2 milliamps. And that makes sense because I have 4 milliamps entering and I have 0.8 leaving and 3.2 leaving. So 3.2 milliamps plus 0.8 milliamps definitely equals 4 milliamps. So yeah, perfect. Cool. So, okay, let's do one more. Now you're going to see why my first problem actually used all current sources for the sake of showing the nodal analysis technique. But let's do one that's got a voltage source in it. You're going to love this. Okay, I have, let's say, 5 volts and 1K, 2K, 3K, 4K. Okay, what I kind of like about this problem is you could solve this using your basic rules. 3K plus 4K, 7K, in parallel with 2K plus 1K gives us the total resistance. Divide 5 volts by your total resistance, find out your current, figure out your voltage drops, and so forth. Okay, so very straightforward problem to solve using our previous analysis techniques. But let's do this with nodal analysis. Okay, so step 1, label our reference node. I'm going to pick this point to be 0 volts. It makes perfect sense in this setup because I have a voltage source, and we've been doing this whole time where this is positive, this is minus, and so this is the lowest point of voltage along our circuit. So easy. All right, let's go ahead and step 2. Let's go ahead and label all of our non-reference node voltages. Well, I have a voltage here. I have a voltage here. And I have a voltage here. Okay? All others are already taken care of. This is 0 volts all along here. This is 1 volt all along here. This is V2 and this is V3. Now, notice about V1. Notice that for V1, I don't have current splitting or dividing or summing. And that's perfectly okay. I still have a different voltage over here than over here. So I don't need to have an actual branch where current is either summing or dividing in order to call that a node and label it. It's anywhere in your circuit that has a different voltage needs to be labeled. Okay, so that's the first thing to note. Now, we've already labeled our reference node and our non-reference node voltages. Let's write out our expressions. Let's write out these KCL expressions. All right, I'm going to start with node V1. All right, someone give me a KCL expression for V1. We want to express V1. Just like we did here, right? Done. V1's equal to 5 volts. It's already given to us by the problem. Okay? This is why I didn't start with this problem. Okay? So V1 equals 5 volts. That's it. We don't have to do anything else for this equation. We are trying to get an equation that we can solve to give us our voltages at the end of the day. Well, in this case, it couldn't be easier. It is explicitly stated here in the problem because I have my reference node here. This side is listed as 0 volts. This side must be 5 volts higher than 0. So V1 is equal to 5 volts. Done. All right, node V2. Now this one we do have to write some currents. And I'm going to pick some currents that make sense to us. V2 here, 0 volts here. Pick it to go down. Current goes from a higher voltage to a lower voltage. Let's make the assumption that V2 is higher. Over here. Now, I know that I'm going to lose some voltage across this 1K, and I know that 5 volts is the highest voltage in this circuit. So V2 should be lower than V1. That's okay. I'm still going to pick this to go to the left. I'm going to not overthink this. I'm actually just going to pick all of my currents to leave because I just can't make up my mind. Okay. So now we have 3 currents. Let's write these out. IA, IB, IC. To the question of reiterate how you got the voltages once you've gotten the equations matrix, I posted a link in the website. You can check out that link for how to solve it with the matrix. I just don't want to lose too much class time for solving systems. Okay, so now let's go ahead and let's write out our KCL equation for IA, IB, and IC. I picked them all to be leaving the V2 node. So let's just go ahead and have them all equal to 0, right? IA plus IB plus IC should be equal to 0. Perfect. Okay, so all of our currents, since they're leaving, you can think of conservation of charge or KCL. The sum of all currents entering a node must equal the sum of all currents leaving a node. You can also think about this as I could write minus IA equals IB plus IC. It'd all be the same thing, okay? So this is perfectly valid to do. Let's go ahead and now let's write out what IA, IB, IC are equal to. IA is going to be equal to, well, use polarity to help you out here. Plus minus. Plus V2 minus V1 divided by 1K. All right, let's go ahead and let's do IB. IB is just going to be V2 divided by 2K. And our last one, IC, is going to be equal to, use the polarities to help you out, higher, lower. Current goes from a higher voltage to a lower voltage, plus V2, minus V3. Divided by 3K. Plug all those back into our original equation. V2 minus V1 divided by 1K plus V2 divided by 2K plus V2 minus V3 divided by 3K all equals 0. And I now have my second equation. The nice thing here is I already know what V1 is. I can just put 5 volts in for everywhere that I see V1 in these next equations. All right, let's do node V3. Okay, for node V3, I'll go ahead and switch up my colors over here. Oh, interesting. Well, I only have 2 currents. We'll pick this one to go down. Okay. What about up here? Pick it to be leaving. If I pick it to be entering V3, then I can just say the two are equal to each other. Or I can go ahead and write it this way, and I can just say that they add up to 0. Either way is going to work. So let me go ahead and just give these guys some labels. And let's say for node V3, I can say that IA plus IB equals 0. Perfect. Okay, so I don't need to have 3 currents or 4 currents. I don't need to have, more than 2. I can do this with just 2 currents here. All right, let's write out what IA and IB are. IA, again, I'll use the polarity. It goes from a plus V3 to a minus V2. All divided by 3K. And for IB, well, I picked this to be 0, so I can just say the voltage drop across the 4K is just V3. Plug those back in. Cool. So what can I do here? I now have 3 equations. Well, technically 2 equations, one that's given. I can plug my V1, which we know to be 5 volts, into this equation, and then I have an equation in terms of V2 and V3, and then I can take these two and go ahead and solve that for my V2 and V3. Once you do that, you are going to get V1 is equal to, well, we already knew that one, 5 volts. V2 is going to be equal to 3.04 volts, and V3 is going to be equal to 1.74 volts. So now you can go ahead. Oh, I did not write those. Sorry. V1 is 5 volts, V2 is 3.04 volts, and V3 ends up being 1.74. Now I can go ahead and plug those back into my original circuit. We had 5 volts. $1K, $2K, $3K, $4K. Okay, so now I know that this was 5 volts over here. I know that this is 3.04 volts, and I know that this is 1.74 volts. And everything was respect to this point being ground or 0 volts. Cool. Okay. So even on our simple problems, and you could have done this with, mesh analysis, or you could have done this with our basic rules. You'll find out that some of these techniques work better in certain situations than other ones. And that's why we kind of learn this full toolkit. That's why we learn Thevenin equivalent circuits, Norton equivalent circuits, source transformation, superposition, Millman's theorem, and you keep on building these up because each one of these tools ends up working better in a different situation. Now, as far as in this class, I will be telling people what tool to use for which problem, but in more advanced circuits, these tools end up just being applied, sometimes just partially, to certain parts of a circuit so you can understand what this section does, and then you can go ahead and translate that, and you sort of build up the full understanding by applying many different forms of these. And in 311, we will see a bit of that, okay? So that takes care of what I wanted to cover in today's class, which was introduce nodal analysis and see these two problems. Both of these problems showed something different, where we had only current sources in the first problem, but in the second problem, because realistically every circuit I've ever seen in life has voltage sources. So seeing it with a voltage source, you saw how easy it was in terms of expressing that voltage because it's practically given. Okay, so I'll leave that there. And then I'll go ahead and stop the recording. I'll take any questions. And then we will go to lab, and if you're still working on that mesh analysis stuff, I will help out during lab. And then to reiterate, the lab is due next Thursday, this Thursday, 10/29, and I updated that on the website because somebody caught a mistake on that. I think I was off by 1 week when I looked at the calendar. Okay, so let me